Assalamu alaikum. Good evening, everyone, and welcome to today's webinar. It's Ahmed from Reservoir Solution, and I'll be your host in this webinar, inshallah. It's our pleasure to have with us Engineer Hussein Al-Ginedi, a senior process and flow assurance engineer with more than 15 years of experience in the oil, gas, and energy sectors. Engineer Hussein specializes in the design, commissioning, flow assurance, and optimization of major projects such as gas processing, flare gas recovery, and power generation. Throughout his career, Engineer Hussein has tackled some of the most critical challenges in oil and gas production, including hydrate formation, wax, and asphaltant deposition, ensuring safe and efficient flow from the reservoir to the processing facilities. Today, he will share his expertise on flow assurance challenges and solutions, supported by real-world case studies and simulation-based strategies. So, before we start, just a quick announcement. Inshallah, we will be sharing in the last 10 minutes of the Zoom. We will share the link of the webinar certificate form in the Zoom chat. Anyone who fills out the form will receive a $10 discount on the course related to this session. Please note that the form will close by the end of the meeting, so make sure to fill it in before we finish. Please join me in welcoming Engineer Hussein Al-Ginedi.
Hello everyone, hope you're doing well. Just please let me share my screen. Can you see my screen? Are you able to see my screen now?
Yes, sir.
Okay. So, first of all, it's my pleasure to be invited by Reservoir Solutions and deliver this introductory lecture about flow assurance in the oil and gas industry. So let's not waste any time and go dive directly into the lecture. First, what is flow assurance? Let's talk about the flow assurance itself. What is flow assurance? The flow assurance is the ability to identify and prevent potential fluid-related problems, such like the hydrate, the wax, scale, corrosion, slugs, and etc., from impacting the production and ensure the successful and economical, and underline this by 100 line, economical hydrocarbon flow from the reservoir to the treatment facilities throughout the reservoir lifetime, through all the lifetime of the reservoir. The fluid properties is the main factor which control the fluid behavior at different pressure and temperature. Each of the multiple areas of expertise encompassing flow assurance can be very specialized. Each point of this in the flow assurance can be very specialized, as they require deep understanding of fluid behavior and verdict of each phenomenon which is going to happen during the lifetime of the reservoir. So, what are the challenges of the flow assurance? The main risks of the flow or the multi-phase flow inside the reservoir itself, inside the well bore, inside the tubing, inside the flow line, are categorized into 4 categories. First of all, the abnormal pressure drop in the system, the tubing and the pipeline plugging, the liquid handling troubles, and also the tubing and piping integrity. We will dive deeper into each one of these, but let's first talk about the specific flow assurance challenges. The most specific or the most popular flow assurance challenges are the tubing and pipe sizing.
استنى كاي
Any problem? Let's continue. Okay, the tubing and pipe sizing, liquid surge and slugging, of course, the hydrate formation, the asphaltene, the wax, the scales and naphtines, the sand formation, emulsion, erosion and corrosion, and the pressure surge. We will talk about each one of these in brief. But just to know, this is only an introductory lecture. We cannot dive deeper into the details of each one, but just we will talk briefly about each one quickly. So the first one is the tubing and pipeline sizing, which means the pressure drop. It depends on the following parameters. The pressure drop in the whole system at different reservoir lifetime, in order to take the maximum recovery of the reservoir. So the pressure drop is matters because we need to take the maximum recovery of the reservoir. Also, the fluid velocity, the pressure drop affects the velocity as it's high. If the velocity is very high, it will may exceed the AVR or the erosion velocity, and of course, it will cause another problems such like the erosion. And also, if the velocity is too low, this will allow for solid deposition, which is another flow assurance problem. Also, the pressure affect the flow regime of the multi-phase flow, as it will be a concern in pressure drop and also in the liquid handling and the hold up of the line. So the sizing of the tubing and the pipelines matters because it will affect a lot of other flow assurance problems. The second challenge or second problem, flow assurance problem, which is the liquid surge or the slug flow, which is the most popular problem in the multi-phase flow assurance systems. So when gas, condensate, and water flows through the wellbore or the pipeline, it will undergo different flow regimes. Depends on the gas velocity and liquid velocity. So the slug flow is one of the not preferred flow regimes on the pipeline, at which the liquid slugs is received to the treatment facilities at limited time to handle and to be followed by a gas phase only. So the liquid surge for the multi-phase flow is critical challenge, especially during the transient operation. So it will cause a lot of problem to your pipeline. It will maybe damage your downstream facilities because the surge volume and the liquid slugs, maybe the system is not designed to handle most of the liquid in the system. So it's very critical to mitigate the problem of slugging in the design phase of the plant in the beginning. The third problem is the hydrate. The hydrate, all of us and you know about hydrate. Hydrate is a solid ice-like compound of water at which the water molecule is hosting natural gas or methane or CO2 molecules inside the water. And this cause a lot of problems such as plugging of the pipeline. And this happens also at the right combination of the temperature and pressure. So there is the hydrate formation curve for the gas. Also, the hydrate formation curve is very similar like this. So maybe the conditions as the well bore, the high pressure and high temperature, you are away from the hydrate formation. And also you may, during the operation or during the flowing through the flow line, you are not even going through the hydrate formation zone. But what if a problem happens in your downstream facilities and shutdown happen for any reason, and the fluid stays in the pipeline for a long time. So especially if the pipeline is going through the subsea system or the seabed, the temperature will go down and exceed the hydrate formation zone, and the hydrate will begin to form. And also, as we mentioned, hydrate is looking for the right combination of temperature and the pressure, which is mainly high pressure and low temperature. This will cause a significant problem in your pipeline, and also will cause maybe the damage of your pipeline and also plugging production loss. This is the most critical flow assurance problem, especially in the gas reservoirs. The other problem, or the next problem or flow assurance challenge, is the wax. The wax is a high molecular weight compounds of the oil, which have potential to precipitate as a solid. As the temperature cool down, the wax start to precipitate and form a layer, as we can see here. This is the seabed and the pipeline, the wall of the pipeline, and inside there is a wax deposit thickness. The most significant problem of the wax it's reduce the throughput of the pipeline. Imagine you have a 26-inch pipeline, and forming a layer of wax on the inside wall of the pipeline will reduce the pipe diameter, pipe diameter, and also will reduce the throughput of the line. Will increase the pressure drop inside the line, will make back pressure to your wells, and also will allow you to lose production. So, if a build-up of solid waxy layer on the pipe walls is allowed to form, it will require periodical removal to avoid the breakage and also to increase the throughput of your pipeline. The mitigation of the wax is done by injecting chemicals, and also by bagging of the entire pipeline to remove the wax layer from the inside or the internal of the pipeline. The next flow assurance challenge is the asphaltenes. Asphaltenes are heavy molecular substances that are found in the crude oil, which is precipitate out of the crude oil because the changes of the process conditions. Asphaltenes can cause reservoir and formation damage, can cause well plugging and pipeline plugging, deposition also in the surface of the facilities. And unlike waxes, asphaltenes doesn't melt. Asphaltenes doesn't melt. The wax can be melted by using the heat or steam, or increasing the heat of the pipeline will allow the wax layer to melt. But asphaltenes cannot melt like the wax. So the thermal methods, such as the insulation, the hot oiling, does not work to prevent or remediate the asphaltenes deposition. So the importance, or the most important point for the asphaltenes, is the asphaltenes flocculation point, which is the pressure at which the asphaltenes first begin to precipitate at a fixed temperature. So asphaltenes are related with the pressure changes, or as we mentioned, operation condition changes. So at this point, the asphaltenes are separated from the resins in the crude oil, as we can see here. And after that, they can precipitate in the pipeline and cause plugging and well plugging, and also can damage the formation of the reservoir itself. The next flow assurance challenge is the scaling. The scale means the precipitation and the accumulation of insoluble crystals or salts from a mixture. Example of the oil scales are the calcium carbonate, and barium sulfate and iron sulfides, barium sulfates, and strontium sulfates. There is a lot of salts can precipitate and cause scales on the pipeline, and also this allow to pipeline plugging and reduce as well the throughput of the pipeline and increase the pressure drop, and also allow to make back pressure to the wells and reduce the production, which is very significant, a critical issue. The next problem is the sand deposition. The sand produced from the reservoir is one of the challenges that affect the system productions, as it leads to the plugging of the wells and the pipelines, and it's also a main factor of the erosion process of the tubing and the pipeline. So the sand can cause erosion to the tubing and the pipelines because of the it moves with the liquid and the gas with high velocity, and can cause the erosion and damage to the pipeline and the system integrity. It can be controlled by installation of sand control system or sand control equipment inside the well, as the sand screen or gravel backing. Those are one of the, as you can see here, one of the sand control equipment can be used inside the well itself. The emulsion is the next flow assurance challenge. The emulsion is the immiscible mixture of oil and water. It may reveal information. The major impact of the emulsion is due to the formation of a stable emulsion. The stable emulsion increase in the fluid viscosity, which can cause high pressure drop in the pipeline. Again, the pressure drop is one of the most significant problems that could happen in the pipeline, as it affects all the production, affect the throughput of the line, affect also the flow regime. So emulsion can increase the pressure drop inside the pipeline. So theoretically, the viscosity of the fluid increases when water volume fraction increases until phase inversion point. And after this point, the viscosity of the fluid reduced with the increasing water volume fraction, as we can see here in the graph. The emulsion can be mitigated through the chemical injection, the emulsifiers, and also by heating. Heating can be used to mitigate the or get rid of the emulsions in the especially in the downstream systems. So the next flow assurance challenge is the corrosion. The corrosion of the pipeline is the oxidation and the electrochemical breakdown of the structure of the pipe. The pipeline corrosion happens through the oxidation of the pipeline or the electrochemical breakdown. The pipeline corrosion can both be inside the pipeline or outside the pipeline, external corrosion. Depends on, inside the pipeline, depends on the fluid properties, depends on the fluid velocity. Imagine if we have, for example, H2S or CO2 inside the fluid from the reservoir, and if we didn't use any corrosion inhibitor, or didn't mitigate the problem of the corrosion, of course it will allow the pipeline to be oxidized and corroded, and this also will allow to a lot of leakages and structure failure inside the pipeline, from even inside or outside. As we mentioned, external corrosion is due to the soil, due to the water, the outside environment of the pipeline. That's why it's very critical problem, and flow assurance allows us to predict the velocities, flow regimes is used to prevent corrosions for corrosion mitigation. The erosion we mentioned previously, the erosion is related to the velocity inside the pipeline. So when the velocity increase for any reason of the gas, for example, it will exceed the EVR. The EVR is erosion velocity ratio. When we reach this limit, the erosion velocity ratio, we start to erode the pipeline from inside. As we can see, this is a sectional picture of the pipeline from inside. Can you hear me? Is the mic is okay? Anyone?
Yes.
Do you have any question? Are we going too fast, or is the best okay for you?
All good.
Good. Okay, let's continue. Yeah. So the erosion happens when the fluid velocity increases, as we mentioned, above the erosion velocity. When the fluid increases above the erosion velocity, and also depends on the pipe material. If there is, as we mentioned, if there is any sand or solid particles inside the fluid coming from the reservoir, this will affect significantly the erosion phenomenon. The final challenge is the pressure surge, which is related to the pipeline integrity. So the pressure surge is a wave caused when the fluid is in motion. Okay, usually liquid, but sometimes it can be a gas when it's forced to stop suddenly. Okay, when you close a valve suddenly, when a control valve failed suddenly, this will cause a momentum change. This momentum change will allow for pressure surge. This phenomena commonly, as we mentioned, occur when the valve closed or pump stops suddenly. This can affect the pipeline significantly and can maybe lead to pipeline damage, which is one of the most critical phenomena. We don't want it to happen in the pipeline. Those were the most significant flow assurance challenges. We just mentioned the highlights. We just mentioned the topic itself. We didn't dive deep on each one. We didn't know the reasons and the causes of each one in details. We didn't highlight how to mitigate all of this in details. Of course, this will be, inshallah, studied in details in the next workshop, in the 5 days workshop. We will take each flow assurance challenge in detail and talk about it, and make also we will make a practical workshop using softwares, flow assurance softwares, inshallah, in the next workshop on the October 15th. So let's continue. What are the flow assurance analysis that can flow assurance engineer do? Of course, first of the analysis is a steady state analysis. Steady state analysis just give you a snapshot of your model, the pipeline, how the pressure will change, how the flow rate will change of the pipeline. You can just make a quick snapshot of your plant using the steady state analysis. Of course, there's also the transient analysis or the dynamic analysis, and it has main role in the following development phases. such as the design and engineering, the mapping of the operation limits due to operation procedures change. And we will talk about this in a minute. And also there is a safety analysis, and we will discuss it later, inshallah. So in the design and engineering phase, so we are focusing on the maximizing of the production window. So the sizing and of the tubing and the pipeline at which we select the base of the pressure drop, the erosion velocity ratio, the liquid held up, and temperature profile. This should be selected during the design and engineering phase. And at this phase, we have to make a transient or dynamic flow assurance study to select the proper sizing of the tubes and pipeline based on the our flow characteristics and our flow line design. Also, the insulation and the coverage. If we need to, if the pipeline need to be insulated due to hydrate formation, maybe due to temperature reduction, if the pipe is going through the seabed, and as we know the seabed temperature is very low, so we have to check if it's possible to insulate or coverage or bury the pipeline under the seabed or under the if we are talking onshore under the sand, if it's required to be insulated or not. This will help us to the flow assurance will help us to mitigate the hydrate and wax formation through the insulation and other solutions. Also, if it's required an external heating, if the temperature will drop significantly, if we require an external heating or maybe heat jacketing, steam jacketing, also to mitigate the temperature-related flow assurance phenomenon such as the hydrate and wax formation. Do we require inhibitors for hydrate, wax, or corrosion? This also has to be decided in the design and engineering phase. How we are going to inject them, and what is the quantity required, where to inject them, what is the type of the inhibitor required. Also, the liquid inventory management is very important. As we mentioned, the slug or the surge volume of the slugs is very significant to be calculated at the design phase in order to size the separators and slug catcher to able to handle the slug volume and the slug slugging in the pipeline. Also, we have to design if there is any pipeline shutdown effect, the pressure shutdown procedures, start-up procedures, ramp up. This also will affect the pressure surge, as we mentioned in the pipeline. So we have to check all of this phenomenon and run we run a dynamic analysis and transient analysis to predict if they are going to happen or not based on our design of the system. And also, if there is any pipeline blowdown, can the blowdown be handled through the system or not? Are the flow velocities are going to exceed the erosion velocity or not? Is there any vibration will happen during the blowdown? Any flow velocity are going to exceed the sound velocity, for example. So a lot of things can be discussed in the design phase of the plant based on the flow assurance modeling and transient modeling in the system. Also, as we mentioned, if we are going to ramp up or ramp down the wells, is there any effect on the liquid management? Is there any effect due to that the turn down ratio of the pipeline will be affected or not? Are we going to exceed the pipeline capacity? Are we going to form hydrate? Are we going to form wax? Also, if there is any ability to pipeline begging, or what will be the effect of the begging on the pipeline? How much slugs we are going to receive by applying the begging on the pipeline? And also the pipeline begging can be in details can be modeled in the flow assurance softwares, and this will be one of our sessions held in the next workshop, inshallah. Will be step-by-step begging modeling in the flow assurance software, inshallah. As we mentioned, the slug management, the well shutdown, all of these are related to the operational flow assurance and the transient modeling in the flow assurance studies, which is made during either the operational phase or the design phase and start up of the system. Also, another type of analysis done through the flow assurance modeling softwares is the safety analysis. Safety analysis are related to the pressure surge. If there is any sudden closure of any valve, pump stoppage, if there is any water hammering, this can be predicted easily through the flow assurance softwares. If there is any pipeline leakage or rupture, what will happen to the pipeline? How to mitigate it? This is also must be done for the safety and integrity of the plant. So, what is the multi-phase flow? The multi-phase flow is the two or more immiscible phases flowing together, such as gas, oil, water, solids, a combination of them. This is multi-phase flow. Multi-phase flow starts from the drilling, as we can see. Through the drilling, there will be a lot of fluids moving up through the tube, such as the mud, the rocks, even the fluid from the reservoir. And also inside the well itself and the well piping and tubing. Also, there will be multi-phase flow, oil, water, and gas, maybe also solids. So the multi-phase flow is present in all the systems or in all the phases of the plant, starting from the reservoir to the flow line and the onshore plant. And also multi-phase flow can be an operation can happen during the operation due to such operation peaking or such slugging or such liquid surge. Is my voice clear? Do you hear me?
Yes, sir, it is clear.
Yes, sir, we can.
Do you have any question, any comment, anything? I feel like I'm talking to myself. Everything is okay?
Yes, sir. Yes, sir.
Yes,
Keep
sir.
going.
Yes,
It's a helpful workshop.
Okay. So the challenges of the multi-phase flow, there is a lot of challenges, especially for the flow calculation. For the single phase flow, the calculations are very easy. You can calculate the gas velocity, pressure drop. Everything can be calculated very easily for single phase flow. But the multi-phase flow, the calculations are very complicated. And most of the oil and gas flow assurance engineers are using a lot of experiments and a lot of correlations to predict the multi-phase flow, to predict the properties of the multi-phase flow. And also due to the instability and how to control the multi-phase flow due to the changes on the velocity, due to the pressure drop, the liquid slugging, the deposition of the solids, there is a complex of flow assurance problems could happen with the multi-phase flow. Also in the separation of the multi-phase flow, the water treatment, the metering, the pumping. So there is a lot of challenges in the multi-phase flow, which make it significant to use the softwares to model the multi-phase flow and to predict the flow assurance problem in the multi-phase flow. So actually, this represents a production system, a typical production system, starting from the reservoir up to the perforation. Then we have the well choke and flow line, and then we go to the process. So after the fluid flow from the reservoir and through the tubing, it's need to be lifted to the surface. So if the reservoir bottom hole pressure is high enough to move the fluid to the surface, in this case, it will have a naturally flow well flowing. So when the reservoir pressure is not sufficient to move the fluid from the bottom to the surface of the well, the artificial lift systems must be used. So after the fluid is arrived at the top, usually it's directed to the downstream facilities, and it may be transported as a multi-phase flow, as we mentioned, liquid and gas and water, and maybe condensate, and also may have some sand. So the driving force that moves the fluid from the reservoir along the production system is the energy available in the form of the compressed fluid in the reservoir. So as the fluid moves along the system components, we have pressure drops. So the pressure in the direction of flow, actually the pressure drops in the direction of flow. So we move, if the pressure is decreasing continuously, the reservoir pressure of the final, the reservoir pressure is the moving force, is the delta B, sorry. If the reservoir pressure is to the downstream facilities is enough, the fluid will move to the facilities by the natural forces. Okay, are you following up?
Yes.
So the drawdown of the fluid is a pressure drop between the reservoir and the well phase pressure. And also, as we're moving up through the tubing, there is a pressure drop inside the tubing due to the gravitational force. And also, each element on the system have its own pressure drop. So we have here the separator pressure.
Switched off.
Any question? Okay. So the separator here as upstream, let's make the separator is our sorry, the mic is interrupted. So the separator is our pressure node at the downstream system. So the separator must be at constant pressure to control the flow through the well. And as the delta B, let's check the chats. Okay, we will go revert back to the question after finishing the presentation. But just let me finish the lecture, and we will answer all the questions after finishing the presentation. So let's focus on the this part, and then we will answer all the questions. So the driving force, as we mentioned here, is the pressure drop between the reservoir and the whole system up to the separator. So the controlling of the flow of the system is the pressure at this node of the separator here. So we have to keep the pressure of the separator constant. If we reduce the pressure of the separator, the flow rate from the well will increase. And if we increase the pressure in the separator, the flow rate will decrease. So we have to keep the pressure at constant value to make a good control through the production system. And also at the pressure increase during the system, there is also temperature increase in the system due to the convection, due to the conductions with the tubing, due to if the pipeline in the seabed of the ocean or the sea, it will also the temperature will decrease. If there is any pressure drop, there is a Joule-Thomson effect that affect the fluid in the moving in the flow line. So the temperature will also decrease during the system starting from the reservoir to up to the downstream system. Temperature in the system changes as the pressure changes, and we need to take care of the temperature and pressure changes. So we have to make analysis of the systems, such like using the nodal analysis. I believe all of you know about the nodal analysis method, which is used by production engineers. I believe all of you studied in the university about the nodal analysis. So this enables the production engineer to analyze and optimize the production systems. We first select a node that represents the inlet, and the node represents the outlet. Here, the reservoir is the inlet, and the separator is the outlet. And we must specify a fixed pressure at the boundaries condition for the reservoir and the separator. Actually, the inflow is the flow from the reservoir up to the nodal point. So we need to describe the flow inside the reservoir from the reservoir pressure till the bottom hole pressure in the flow curve, which here is in red color. So represents the pressure loss inside the reservoir. So the pressure at the flow rate of 0 is the average reservoir pressure, which what we should expect when the well is in shutting condition. So that the flow rate increases, the pressure loss increase in the system. As the flow rate increases, the pressure loss increase in the system. So likewise, the outflow curve represents the pressure losses in the well and the service facilities. So as the flow rate increase, we need higher bottom hole flowing pressure to be able to lift the fluid up to the separator. Between these two curves, intersection between those curves showing the operating point at which theoretically how the system will have or capable of producing this point, the intersection. So we can then use as a basis to examine the ways to increase the production. For example, if we did hydraulic fracture, the fracture affects the IBR, the well, and reduce the well skim factor, and will shift the inflow curve to the right, and this will increase the productivity of the well. So likewise, if we install an ECB, if we install an ECB pump, it is shifting also the curve of the outflow, and also will have the similar effect on the increasing the flow rate of the well. So why multi-phase flow is preferred? There is a lot of problem can be caused by the multi-phase flow. So why we are going to use the multi-phase flow? Why we are not separating the fluids in the subsea? Why we don't install a subsea separator to separate the gas from the water and make the flow through the pipeline single phase flow and get rid of all this flow assurance problem? The main reason is the economical reason. We install different subsea systems in different locations, maybe, or if the reservoir have different drilling locations, we have to install subsea separation in each location. This will be very costly, and the capital cost will be very high. So now the flow assurance softwares made our life easy. So we can make your flow assurance model and keep it running during the lifetime of the plant. And this will reduce significantly the capital cost of using the subsea system. As we mentioned, the multi-phase flow can be very challenging because it can have gas and water droplets, and it can has gas and condensate and sand solids just like hydrates, wax, asphaltenes. So the multi-phase flow is very challenging. Let's check the next experiment. This experiment was made on Schlumberger Cambridge flow loop. This is a 6-inch pipe with 115 barrels of oil per day and 115 barrels of water per day, with a specific with the viscosity of the oil 1.5, more or less like the water. First of all, we used the perfectly horizontal pipeline to demonstrate. We made the oil in red and the water in blue color. Let's see. Let's check what happened during the experiment. First of all, the perfectly horizontal pipeline, you can see the phases are moving at the same velocity, with a very small velocity difference at the interface. However, if we increase the pipe inclination by 2 degrees, it might be noticeable. Let's check the and we increased here the inclination by 2 degrees. Let's see what happens for the multi-phase flow. It's just oil and water. You can see here the oil is moving so fast. The oil is moving so fast, and the water is accumulating at the bottom of the pipeline. So what if we made the inclination 2 degrees downward on the other side? Let's check. Remember, the oil is in red and water in blue. Here. So you can see the water is moving very fast. Just this is 2 degrees inclination. 2 degrees inclination cannot be noticeable by the human eye. So what about if we increased the inclination by 45 degrees and added some gas to the pipeline? Let's see what will happen. Of course, we will have a mess like this. It's very complicated. That's why we need the simulation to describe the multi-phase flow inside the system. We cannot just use Excel sheets. We can use the small correlations to represent the challenges in the multi-phase flow. It must be used by experiments and correlations and software to describe the multi-phase flow. Imagine what will happen along a very long pipeline in the subsea system with different inclinations, different angles, and different flow rates, different pressures, different temperature. There is a lot of challenges and cannot be easily predicted by correlations or by just steady state simulation. So when we have gas and liquid in the pipeline, and when the liquid completely fills a pipeline at times alternated by when the liquid only partially fills the pipeline, we might have a slug. We will talk about slugging later, and we will talk about slugging in details in the workshop. But the flow will be in complex issues, and the flow regimes will not be easily predicted. So the phase envelope, which can start with single phase flow. Some points we can start to have multi-phase flow. There is also the liquid hold up in the pipeline. So generally, the gas will travel faster than the liquid. So the gas, as the gas is lighter and less viscous, so the liquid is held up compared to the gas. And I will show you some videos. Finally, there is a pressure and temperature change in the system, which will affect this kind of multi-phase flow problems, and significantly more complicated than the single phase flow problems. As we can see, there's hydrates, there is scale, there is asphaltenes, wax, and also we have to predict accurately the analysis or the composition of the flow to get the right results from the simulation. So among the different multi-phase flow, the most common is the two-phase flow. Two-phase flow is liquid and gas, solid and gas, two-phase flow. And among the different two-phase flows, gas and liquid are the most commonly phase flow encountered. And this takes us to the flow patterns or flow regimes. So in the flow assurance, flow regimes refer to the characteristics pattern or the distributions phase between the phases, such as the liquid and the gas, within the multi-phase system. The regime is directly determined by factors such as the phase fraction, how much liquid, how much gas, how much solids, the flow rates of each one, the physical properties, the density, the viscosity, surface tension, and also the most significant is the pipe geometry. So if we talk about the horizontal line at low velocities, where there may be stratified, so we have a gas phase and liquid phase. Each one is moving alone, as we can see here, as the flow of the gas increases. So it forms waves, so it can be stratified wavy when the flow rate or the velocity of the gas increase a little bit. As also when the gas is very quickly passing along the pipeline, it can form the plug or slug flow. And at higher liquid flow rates, the gas can travel quickly through the middle. It can be annular flow. And at very high liquid rates and very high liquid rates can cause the slugging and slug flow, and maybe also plug flow. And a very low liquid flow rate, it will be annular flow. Okay, this is for horizontal pipelines. So in the vertical pipelines, liquid more liquid than the gas, we can, if there is more liquid than the gas, we can get the bubble gas, bubble flow. It's a lot of liquid and less gas volume. And if there is a greater gas volume, the bubbles will come together and form a larger bubbles, which can be a churn flow or a slug flow. And also, when the flow rate of the gas reduced, the slug flow will be the dominant flow. Determining the whole liquid is in the pipeline, the liquid hold up in the pipeline is very critical because, as we mentioned, it can cause a pressure surge and can cause slugging in the pipeline, and also can cause significant problems in the downstream system, such like the separators and the slug catchers, as we mentioned before. So as we increase the flow rate, we need much less upstream pressure to push the liquid from the upstream to the downstream. So because the higher gas velocity means the liquid is being swept more efficiently, and there is less liquid hold up in the pipeline. So as we increase the rate further, we reach a point where the friction starts to take over. So we end up with more and more frictional and pressure drop, which require higher and higher inlet pressure to deliver the required pressure downstream the system. So the hold up depends on the velocities of the gas and the liquid, and also depends on how much volume fraction of the liquid inside the pipe line. We will talk about it in much more details, inshallah, in the workshop. And excuse me, I know the time is too tight, so I cannot talk about everything in details, and I have to leave some loose topics. Here, there is a relation between the inclination of the pipeline and the slugging and the hold up of the system. As the flow rate increase, as here the flow rate increase, the flow rate here, we have three flow rates, 16 kilogram per second, 32 kilogram per second, represents in the curves here. As the flow rate increase, the hold up in the pipeline increase, as the flow rate increase, the hold up decrease in the pipeline. So as the flow rate increase, we mentioned the velocity will increase, and as the velocity increase, the slip ratio will increase, and the hold up of the inside the pipeline, the liquid hold up will decrease. So what is the hazards of unstable production due to the multi-phase flow? As we mentioned, there will be a lot of damage inside the facilities due to the surge volumes and surge pressure, and also there is instability in the production. There is increase in the corrosion rate. Imagine that you are having a downstream facilities with compressors with a lot of equipment, and you receive a sudden slug of water or sudden slug of liquid. This will cause a lot of problems to your downstream system and will affect the downstream system significantly, and you may lose a lot of production in the system. So what are the types of slugging? We have three types of slugging in the systems: the hydrodynamic slugging, and the terrain slugging, and the operation slugging. The hydrodynamic slugging is related to the flow regime and the flow rates and the velocity. The terrain slugging is related to the geometry of the pipeline. So if there is a riser, the flow regime will change, and also the slugging may occur due to liquid accumulation. Also, the operation-induced slugging are created by the system, maybe during the ramp-up of the wells, digging, any operational issue related slugs. Let's continue. As you mentioned, train sluggings are related to the geometry of the pipeline. So if you have a riser, liquid will start to accumulate until the pressure of the gas is able to push the liquid, and this will cause a slug. In this case, it's called terrain slugging. The operational slugging, as we mentioned, due to the ramp up, due to the begging, due to the operational procedures in the plant. So imagine you are having a pig inside the pipeline. It will remove all the liquid from the pipeline down to the downstream facilities. And of course, it will have a significant liquid slug in the pipeline. Also, there is a turn up slugging when you increase the flow rate or ramp up the the production from the wells. This will increase the gas volume inside the pipeline, and also will remove some liquid from the bottom of the pipeline, and this will also cause a significant slug in the pipeline. Lastly, what is the liquid surge? Liquid surge is the powerful movement of a given quantity of water, which comes in suddenly through increasing liquid rate suddenly through the, as we mentioned, operation or begging or something. And the surge volume, which is a difference in the volume or the slug volume, which we can receive or enter the slug culture in the downstream facilities. This takes us to the most important topic in the flow assurance, which is the fundamental of the petroleum chemistry. Of course, as we know, if you are going to make a model or make a simulation, you have to respect your plant. You have to respect the characteristics of your flow. If you entered a wrong properties or wrong characteristics of your flow, of course, you are not going to have a good results. Of course, you are not going to detect the problems in the right manner. So understanding the fundamentals of the chemistry of the petroleum and the gas is very important. And that's why we are going to have a dedicated workshop related to the PVT system. We will also going to use some softwares to generate the PVT files and to use the PVT files to make the flow assurance models. And this will also be indicated in very detailed in the workshop, inshallah. So it's very important to understand the composition of the crude oil in terms of elements, in terms of the compounds itself, the paraffins, the naphthenes, the aromatics, the asphaltenes. Also, it's important to know what are the impurities in the crude oil and what are the significant problems that can cause to the systems and to the downstream facilities. So the most important characteristic is the phase behavior of the system. So we will learn how to generate as I mentioned, the PVT file and the phase diagram of each separate different location. You can generate your own phase envelope and predict the different characteristics of the fluid, gas, oil, or condensate, or whatever. How to generate the PVT file based on the conditions of the reservoir, based on the conditions of the wellhead, based on the conditions in the separator, how to make it perfectly right to your simulation, how to know is this the right PVT file or not, is this the right composition or not. This will be covered, inshallah, in details in the workshop. Again, excuse me for going very quickly through this presentation. The webinar is only 1 hour, so I cannot go in very deep details for each specific element. That's why I believe I couldn't deliver the most important sides or specifics about the flow assurance studies and modeling. So inshallah, I will be with you in the workshop, and I hope I can answer all of your questions, and we will be hand by hand and doing the workshops using the softwares. And I will make sure that you understand each and every specific detail about the flow assurance challenges and flow assurance modeling, starting from the steady state simulation to the dynamic simulation or transient simulation, and also the safety analysis. So that's it for me. That's wrapping up our presentation. Let's check if you have any questions in the comments. I will try to answer your questions quickly. So let's stop sharing my screen, and then I will read the comments and try to answer your questions, inshallah. Thank you. So Mazid Ibrahim is asking, how does asphaltene precipitation differ from wax deposition and how it is managed? So as I mentioned in the beginning of the presentation, each specific challenge in the flow assurance can have a multi PhD studies in it. And wax is very, very different from asphaltene. Wax is mainly paraffins, mainly paraffins, and asphaltene is different compound from paraffins. And inshallah, we will describe in details every one of them in the workshop, and how to mitigate it, and how to manage each one of them, how to predict each one of them, how to inject the proper chemical to get rid of them. So any other question? Can pressure surge phenomenon also be the same as
Hello?
water hammer? Yeah.
Yeah, could you provide PPT?
Can you raise up your voice, please?
Could you provide PPT regarding the class?
BPT, by BPT you mean a software or a BPT file or?
Well, PPT,
Sir,
sir,
slides.
PowerPoint presentation slides.
Yeah, of course. As I mentioned, we will cover the BPT in details in the workshop, inshallah, and we will take it step by step how to generate the BPT, how to use the BPT in the proper manner, how to use the BPT inside the flow assurance software, how to change the BPT if required, how to add components such like the MEG or monoethylene glycol for hydrate inhibition, for example. This will all be covered in details, inshallah, in the workshop.
Okay, thank you very much, Mr. Hussein. Can I ask just a few questions?
Yeah, of course, go ahead.
Okay, thank you very much. My name is I'm called Mark, and I'm a research scholar. I'm based in India. So basically, I was asking about you have described as the flow assurance and also the multi-phase. Thank you very much for the presentation. It has been nice, but however, I wanted to inquire what softwares are used in the flow assurance, and are they open source as well? Can they be accessed? And secondly, we have had advances in machine learning, artificial intelligence. So are there those advances in flow assurance in terms of
You need to
computation
know
and
what
modeling.
you need to know what are the softwares for the flow assurance in the industry.
Yes.
The most popular software in the industry, the Olga software, of course, and also there is other softwares. Let me remember the name. I think it's Linda. Or there is a lot of other softwares can be used for flow assurance, and also for the BVT. There is multi-flash. There is other softwares in the industry can be used for BVT. LIDA Flow. LIDA Flow is the other software like the Olga. LIDA is the other software, and there is also another softwares can be used in the flow assurance studies in the industry. A lot of softwares. Yeah.
Okay, thank you very much. Can I ask another one? I've also inquired if there are advances of because we have advances in machine learning and artificial intelligence. So I don't know if there are advances of research work that has been done in terms of computation and modeling in terms of the flow assurance.
Recently, Schlumberger has introduced an AI model builder inside the Olga. I think they started to implement the AI and the machine learning inside the Olga, and can be used but if you have the license of the program, you can use it. Yeah.
Okay.
So, any other question?
Yeah, basically that's it. And maybe the last one could be the future of young professionals in terms of the field of the flow assurance studies.
Again, your question, please.
What is the future of young professionals in terms of the flow assurance studies? Like,
I got it. Yeah, the flow assurance is very promising. And now I can see a lot of vacancies and positions for the flow assurance engineers, especially if you are specialized in a topic such like the hydrates, such like the slugging, the asphaltenes, the wax. There is a promising. It's a promising specialization, and I believe it will be very important during the next years, inshallah. Any other questions? Muhammad is saying, is the next section related to chemical engineering sections? Yes, of course, it will be related to the chemical engineers. We will talk about all the flow assurance challenges in details, and we will talk about as we mentioned, the BVT. We will build models, flow assurance models, steady states. We will build dynamic and transient flow assurance model. You will learn how to build those models in your own. And also you will learn the basics of the BVT and multi-phase systems, inshallah. Any other question? In the study of the emulsion on viscosity, how can we replicate the emulsion in the lab mixing oil, water, and see the droplet size? Of course, you will have to take lab samples. You will have to take samples from the system. And also I have seen some flow assurance engineers using a stream-fold former and change the viscosity of the stream to match with the operation conditions, the pressures and temperatures and the flow inside the pipeline to replicate the effect of the emulsion and try to simulate it and mitigate the problems of the emulsion. It can be done through the flow assurance modeling also. Can ANSYS software make a good prediction and information flow assurance analysis? And ANSYS is more related to CFD analysis, maybe related to the design of the nozzles, design of the pipeline geometry. This will help in the flow assurance analysis, but will not such in very specialized area, and also will not help in the other challenges, such like the hydrates, such like the wax, the asphaltenes, the corrosion, erosion. So it can be used, but for just a very specific area. Any other question?
Assalamu alaikum, sir. I wanted to ask you about the hold up. How is it a critical issue or a problem in flow assurance, like other wax deposition, sand, and asphaltene? How it is common in flow assurance to deal with, and is it a critical issue to deal with?
Of course, as you mentioned, the hold up, increasing the hold up will increase the slugging. If you ramp up the well, increase the production, make the begging for the line, you will have to remove all these liquid from the pipeline. This will cause slugging in the line, and also will cause a significant liquid flow to the downstream facilities. This is a very significant flow assurance issue and can be mitigated through the design at the first place, as we mentioned, by installing the proper facilities such as the slug catcher, and also through the operation phase. You can run a simulation, a transient simulation, to predict how much liquid you are going to receive in the downstream facilities. And this by adjusting the flow rate, adjusting the step or the ramp up step, you can adjust the amount of liquid received in the downstream facilities, or the amounts which you can handle in the downstream facilities. That's why the modeling the slugging is very, or modeling the hold up in the line is very critical and very important, of course.
Thank you, sir. Thank you very much.
You are welcome. Is there any other question? So I hope you enjoyed the presentation. As I mentioned, sorry for going so quickly, but inshallah in the next workshop we will be explaining everything in details, going step by step, trying to give you all the required details to build your own flow assurance model in the plant, inshallah, in your plant, inshallah. Thank you, and I will leave the mic to Ahmed. Thank you, Ahmed.
Thank you very much, Mr. Hussein. So we came to the end of our webinar today. Thank you all and wish you a good day. Assalamu alaikum.